In this session, I will continue speaking about the different concentration technologies, and I will refer to the most promising ones, the parabolic trough configuration and the tower configuration. Again, remember that any questions can be posed through email, either to Rafael or to myself, and you have here the email address of both Rafael and me. The most popular technology worldwide on CSP is the parabolic trough. In Spain, there are more than, I say 48, I think it's 47 plants are in operation in Spain having this technology. And also some of the plants in the USA, the ones called the SEX or located in the Mojave Desert, they have been in operation since the 80s. So is the typical proven technology, and this looks banal for an engineer, but when you go to a bank and you are asking for a loan, believe me, it's very positive to have some proven experience already in the worldwide somewhere, operating for 30 or more years. The plants are, let's say, pretty standard. The construction of the troughs is pretty standard, and obviously is the easiest way of achieving the loans from the bank. Bankability, again, is a concept that is very important in this kind of projects, mainly because they require a huge investment, and this kind of investment only can be provided with the support of the banks. Most of the plants in the having parabolic trough today are plants using molten salts as a media to store the energy to be able to produce in a much more regular way, in particular to produce during the night. Some of the plants have been installed just providing steam to another systems like a coal plant or a combined cycle plant. Then they generate some additional steam to the plant, and this is a way of save fuel or to make the operation cheaper, even having to support the cost, the additional cost of the solar field. And something I want to say is that this is, as I say before, a proven technology and has been heavily industrialized. Just to mention that Sener has made something like 2,500 kilometers of this kind of structure holding the mirrors. So obviously, having the expertise of producing something like 2,500 kilometers of this device, the prices have become much cheaper as compared to the initial ones. The way it works, obviously, this is a mirror, but the mirror has been bent to a parabolic shape. And then when in operation, this is not in operation, the surface is facing the sun. So the parabolic shape is reflecting the sun rays and concentrating the sun rays on this tube. And as you can see, the tube is actually a sandwich of two tubes. One is the stainless steel inner tube. Inside that, you will be passing the oil. And then there is an external tube made on glass. And in between the two tubes, they produce the vacuum. So this is obviously to minimize the heat losses in between the inner and the outer tubes. So let's say that from the thermal standpoint, it's a very isolated system. The misadvantage that I hate is that obviously this pipe needs to be tracking the sun. Means that during the day we'll be moving like that. However, the installation, the piping installation providing the oil to the trough remains static on the ground. So you have to use a flexible connection in between the static part of the pipe and the part of the pipe which is moving. And this is obviously a weak point in the installation. I hate that. I hate the swivel joints. I hate the flexible connections. I like this picture because it shows that even this maybe is in operation, this trough is maybe in operation. You can see the light concentrate on the tube. So maybe inside the tube you have oil at 400 degrees. However, you can see the birds just standing on the outer part of the glass tube, and you can see that the insulation is so good that even when this is 400 degrees, the surface temperature is very, very low. Yeah, this is the sex. This is the plants made in the late 70s and the early 80s in the United States in the Mojave Desert. Well, there are some areas of the plant that are looking better than this one, this picture. I took that picture on purpose to show something which really is damaged. You can see the pieces of glass missing. You might see that some of the tubes are naked. I mean, they have lost the glass cover. But it's still, those plants, well, you can see that everything was made like 34 years ago. But still the plant is in operation, even when you can see that the insulation has been lost here, that well, everything is a bit old and not properly maintained. The plants are still well concentrating the light on the tubes and generating good heat, which is later on transformed into steam to produce electricity. I also like this picture. This is the first non-commercial but prototype of center trough. Here you see the old-fashioned trough that was used, for instance, in Andasol 1 and 2. And then in Andasol, we created a special trough, and we created a loop to test the new trough, which, as you can see, is composed of a piece of pipe, and then those pieces are just pieces produced from a tin plate by extrusion. It's not called extrusion. It's like pressing the tin plate to produce that shape. And obviously, this is easier to assemble, and it is far cheaper as compared to the welded structure that is substituting. Here you have how it looks like. I mean, well, this is the finished device. I mean, this is the those are like 12-meter pieces of pipe, and then you have those pieces that are bolted to the main pipe, and the pieces are made of very thin tin plate, very thin tin plate. So this is the structure. Even the supports for the pipe, for the collector, also are made from stamped steel. So it's a very lightweight configuration compared to the previous one, and has to be very good. I mean, the Cerner people say, oh, well, low manufacturing cost, low assembly cost, high repeatability, high performance, good durability. All that has to be true, because in fact they have been able to sell today more than 2,500 kilometers of parabolic trough. It's a big figure. I mean, 2,500 kilometers is the distance from here to Paris or something like that. So imagine assembling a road, a highway 7 meters wide of moving glass, making a distance from here to Paris. I mean, it's impressive. I mean, it's the amount of troughs that were produced by Cerner in the last 3 or 4 years. I would like to have stocks of Cerner, by the way. And which is even better is that they are not able to sell this trough only in the plants where they are the, let's say, the main contractor. But for instance, all these plants here having a lower number of loops, those are plants in which Senair was not the major contractor, but these plants were made by engineers competing with Senair. However, they recognize that the Senair trough is by far the fastest and cheapest way of concentrating the light, so they were buying the Senair trough to their competitors to be used in their plants. I've been working for Andasol 1, I've been working on Andasol 2, on Estresol 1, and then I moved to Torresol. And believe me, at the beginning, working for Senair in Gamma Solar, I was a bit skeptical, meaning that, well, we are world leaders in parabolic trough technology. We have developed the molten salt technology for parabolic trough. We have the best technology in the world regarding CSP. Why to move to the tower configuration? And honestly, I have to say that very soon I was converted into the tower configuration, and right now I am absolutely in love with Gamma Solar, with my dearest Gamma Solar. First of all, it's a very nice looking plant. I've been there with many visitors, and well, you can see how it looks when in operation. The plant is composed of heliostats. Every heliostat is adopting a different angle. I think in this picture you can clearly see that every heliostat has a different angle because their function is to reflect the light of the sun and concentrate the light of the sun on top of the tower. And when in operation, you can see something like that. I mean, there is a huge concentration of light here. This is the equivalent to 140 megawatts of thermal energy. You cannot look directly to the spot. I mean, the light is too intense. You need to use some dark glasses to look to the receiver, because inside the receiver, I mean, where the light is concentrated, you are reaching a level of radiation which is similar to what you get in a welding machine. I mean, you know that you cannot be looking somebody who is welding metal. This is exactly what happens here. I mean, we have a huge concentration of energy or light, and I have to tell you that this receiver located here is not white, is black, is matte black. It has been designed to be absorbing all the energy and not reflecting anything. But you can see that obviously when receiving that huge amount of radiation, even the black, matte black object is reflecting a lot of light, and this is what you see. The process in Gamma Solar is very, very simple and very simple to explain. What we have obviously is not two heliostats, we have 2650 heliostats, 2650 heliostats. And each one, I repeat again that each one has to adopt a different angle to reflect the light of the sun and concentrate the light of the sun on the tower. Here we get a huge 140 megawatts of thermal energy in good conditions. Obviously this spot will be melting in seconds in case that we don't have any cooling to prevent that system to melt. The cooling is provided by what we call cold molten salt. And well, it's a strange expression because in our case, cold means 280 degrees Celsius. Then we take liquid salts, molten salts, and we pump them to the receiver. The receiver is again like a radiator, so the molten salts are passing through the radiator and are absorbing the solar energy. When exiting the receiver, they are at 565 degrees, and we control the flow by using variable speed pumps to maintain 565 degrees, a constant temperature at the exit of the receiver. Okay, so the process consists in reflecting the light, concentrating the light here, and simply pumping salts to absorb the energy and increase the level of this tank. And that is the end of the solar process, because the next step in the process is just to convert that energy that we already have gathered, that we already have in the tank, into electricity. And we do that by taking hot molten salt from here. We pass through not one, but we have a battery of heat exchangers to produce high pressure steam, which is delivered to the turbines. We don't have a single turbine, we have a high pressure turbine and a low pressure turbine, etc. But to simplify the process, from the hot molten salt tank, we provide energy to water to be high pressure steam, which is delivered to the turbine, and then the turbine is connected to an alternator that provides electricity. Obviously, after providing the energy to the steam, the salts are going to be returning to the cold molten salt tank, and then again to be pumped here, and so on and so on. But the good thing about this process, which makes Gemma Solar unique in the world, is that the turbine and the alternator are not facing the sun. They are not related to the sun. They are operated according to the level of salt in this tank. Meaning that if at 3 o'clock in the afternoon I have a cloud avoiding any radiation at 3 o'clock in the afternoon, the turbine is not going to realize that fact. I mean, the temperature here is going to remain the same. The flow is governed by a pump, which is here, which is not related to the sun at all. So even small variations in the radiation during the day will not be affecting the performance of the turbine. The turbine is only affected or related to the sun when the molten salt in this tank is reaching the minimal level. Then obviously you have to stop the turbine. But we have in this tank enough buffer to operate the turbine for 16 hours. So when this tank is full, that happens mainly during the summertime, we reach a moment in which the tank is absolutely full. We are not concerned at all, because we know that in the next 16 hours we can produce electricity without any radiation, without whatever happens. We know that for the next 16 hours our production of electricity is going to be guaranteed. Again, I'm absolutely in love with the tower configuration, and I will refer only to the advantages, because I don't see too many disadvantages. First of all, in that system, every pound, every kilogram of molten salt is holding a lot of energy, because the T differential is between 260 something degrees to 565 degrees. Then storing is so cheap that you can design plants to be operating 24 hours. But operating 24 hours means that you are not stopping the turbine and starting the turbine every day. That means that the turbine life is going to be enlarged. Obviously, it's good to produce 24 hours a day, because then your asset utilization and the return of the capital is going to be faster than when operating 1,800 hours per year. We have very low operational costs. We have nobody running to see what happens with one of the pipes or one of the valves in the solar field, simply because we don't have any liquid. We don't have any valve in the solar field. all the piping system is just around the tower in a radius of 60 meters. So maintenance obviously is far cheaper as compared to the maintenance in a traditional plant in which the solar field is invaded by fluids. We operate, we don't have the limitation of the oil, so we operate with the maximum temperature. In fact, we operate with steam at more than 550 degrees Celsius, and this is the same temperature as used by the most efficient coal plants, for instance, in the world. The turbines are just standard turbines because we operate with the standard conditions for the turbines. To me, everything is advantage. Again, I'm willing to answer your questions, if any, on this subject.